Swayam Prabha. Digital India. Educated India.
Welcome to the course Environmental Impact Assessment. In this session today, we are going to cover second part of method for environmental impact assessment considering air within the larger ambit of EIA methods. So we have been covering EIA methods for some time. In the previous session, we covered the concept and the screening stage, and we also looked at different standards. So today we will cover impact prediction and evaluation stage while we look at how we assess the environmental quality with concern with air. So accordingly, the coverage under impact prediction and evaluation will include, we'll look into the background of it, we'll look into the physical models and the expert opinion which are used, as well as we'll look into numerical dispersion models. We'll look into principles of air pollution dispersion modeling, what's the idea behind it and what rules we follow. Then we'll look into road traffic air pollution modeling. Further, we'll look into what kind of data is required for modeling purpose. So what is the input data we given? Then we'll look into the model output. Further, we'll look into the limitations of the modeling. Further, we'll also look into order effects concerning with the air quality. Then we look at how we assess the significance of our results, whatever impact we get, how do we look at the significance of those impact. Further, we'll just briefly cover one of the case study. So accordingly, the expected learning outcomes are that you should be able to review the purpose and you should be able to identify and choose which method to use, such as the physical model, or you need to use have expert opinion, or you need to look at numerical dispersion models. Further, you should be able to review the principles, the underlying principles of air pollution dispersion modeling. You should be able to list road traffic air pollution modeling tools which are available to you. You should be able to identify the modeling inputs, like what kind of data is required, from where you'll find those data. You should be able to review the model outputs. So once you get the model output, you should be able to see what it says, and then further you should know what to expect after you have done modeling. You should be able to state the model limitations. So when you are using certain kind of tool, you should be able to tell about its limitation and then accordingly make judgment. You should be able to review significance of the impact identified through different methods, and you should be able to explain all of these with the help of case study. And further, you should be able to also tell about the order effects and then the method available for that. Our textbook for this purpose is Therivel and Wood, which we have been following. For this particular segment, you may read chapter 4 for reference purpose. So looking at the methods for impact prediction and evaluation, first option available to us is that we see the physical models and the expert opinion. We see that occasionally physical scaled model is being used with combination of wind tunnels, and we also see usage of computer graphics for impact prediction and evaluation. In particular, these are used in conditions where topography is complex, such as hilly terrain. Also, when numerical models indicate uncertainty So whenever you use a numerical model, it indicates certain level of uncertainty regarding the pattern of effects due to the surrounding buildings and terrain. So in those conditions also you use the physical model or the computer graphical model. In the image, you can see the physical scale model in wind tunnel. The study consisted of two phases. In this particular case, you can see we are estimating the turbulence and they are also looking at the pollutant dispersion experiments. So link to this study is provided to you. So if you are interested in learning more about it, the link is given here. You may also use expert opinion with the justification for the opinion. Whatever opinion is given, you need to justify it, and this can be used as a predictive method. Expert opinion is important in the process, particularly at the early stage of the project design. It is important for any type of project. It is also cost and time effective when you have similar projects to learn from. You can also use the analogous method by comparing with such similar existing developments or planned projects for which prediction has already been undertaken for the purpose of estimation. Next we see is the numerical dispersion models. Numerical dispersion models are the most used for the purpose. Through the model you can calculate how specified emissions rates are transformed by the atmospheric process into pollution concentration at different distances from the source or sources of pollution. The pattern can vary with the atmospheric process of dilution and dispersion and can also be transformed sometimes because of the chemical and the photochemical processes. We see that models are also used for predicting pollution concentration for emissions from single point source. For example, from the industrial stack, the chimney which you see, or the vent, and also from emissions from a large number of point source simultaneously. Example, ponds, setting tanks, and then open cast mines or quarries. The basic model which are available while you use it can be further enhanced in accuracy, how they predict, like by adding site-specific complexities into the model, site-specific complexities such as like flat or hilly terrain. Then you can also add surface roughness, example urban or rural conditions. Then you can also add effects of sea breeze in the coastal area. Then even the presence of nearby buildings which may cause building wake effects can also be added to the basic model. You may also find models for area source. So area source such as construction sites, car parks, motorway service stations, industrial processes which has numerous vents, urban areas, and the metropolitan areas, storage lagoons, and so on. So these all are the area sources. So you would find models for that as well. Then you have line source, for example open roads. You can think of the open roads where there are vehicles, continuously moving vehicles, the railway tracks, and so on. Then you also have volume sources such as the vertical area sources with vertical depth. For example, leaking gases from a group of industrial processes, then the takeoff and landing activities of an from an airport. For the odor, now we are going to look at the odor, the smell. The effect can also be predicted by point source dispersion models. It can be done based on the emission of a pure substance or in terms of emissions of odor units. So you can tell it by the units as well. We see that both simple and complex advanced version of numerical dispersion model exists, so you can use from either of them. Simple models usually are known as the screening models, which are used for the screening purpose, are designed for use as an inexpensive tool to identify whether or not air quality, further investigation into the air quality is required or not. In the screening models, very simple assumptions are taken, simple assumptions about the behavior of pollutants in the atmosphere. They can be used with the limited meteorological input data, such as minimum and maximum ambient air temperatures and minimum wind speed, with which worst case pollution concentrations can be estimated. If you see in the screening model that emissions from a proposed development are producing air pollution concentration, the results are minimal, they are considerably below the standards, then you may not go for further detailed or more accurate investigation, and therefore you would not really require complex models. There are screening models which are available, like US has EPA's Screen 3 and AER Screen. These are the examples of screening models. However, it is suggested that irrespective, like you saw, that if the result is minimal, below the standard, then you might not go. But it is suggested that if there is a major development, then irrespective of your result, you should go for a complex model. Examples of complex model include EPA's CalPUF and Air Mod dispersion models, and then you also see another model from UK, ADMS dispersion modeling, which is available. In the image, you can see the snip of Support Center for Regulatory Atmospheric Modeling, where they provide info on air quality models, modeling applications and tools, guidance and support, meteorological data and processor. They also provide training and resource support. So the link is provided to you and you can visit this website. It is indicated that the usage of US EPA models is very high, widespread, and you can see it is used in Australia, New Zealand, Canada and South Africa. Furthermore, they have the usage is high because they have open access to the source code through this particular support center, and we also see that there are certain commercial versions also available. For example, you have CalPUF View, which is commercial version, which uses like it's very user friendly and in terms of input and output routines which are available with them. Now we look at how do we really choose the dispersion model. Selection of a dispersion model will depend on our what are your requirements, what exact requirements are there for assessment. For example, for modeling industrial emissions, you may require permit to operate. Also, regulatory authorities may also have specific requirements regarding what type of modeling software you may use, what would be the input data and what will be the modeling procedure. So, you need to decide based on this. You may also follow a very general guidance that bigger and more complicated the installation, the project you have, you would require a complex dispersion model. Example of model for impact prediction as suggested by the Ministry of Environment, Government of India, like the list has been provided to you. You can just see that how they are telling about all the models which are available and then how it can be applied and what kind of information can be extracted or what kind of input or output data can be taken out from here. So you can see, you can go through the entire list. I'm just going to read out one of the details from here. So you have model ISCST2, which can be applied for 4-point area and line source as well, and it's applicable for flat or rolling terrain also. And then you have transport distance up to 50 kilometer. Then you also have it computes for 1 hour to annual averaging periods. Then you see that it can take up to 99 sources, and it computes concentration on 600 receptors, like where the impact will happen, and it does it in the Cartesian or polar coordinate system. It can also take the receptors elevation, requires source data. It also needs meteorological and receptor data as input. So all these details are provided to you. So likewise you can see all the you have seen the list of models which are available to you from the Indian context as well. Now we'll look at the principles of air pollution dispersion model. So on what basis, what are the underlying principles on which all these modeling is done. So we see that mostly the numerical prediction models are developed based on the Gaussian assumptions. In case of point source of pollution, for example, chimney stack, the basic Gaussian model considers that the pollutant emission spreads outward from a source in an expanding plume aligned to the wind direction. So it goes in the wind direction. It spreads in such a way that the distribution of pollution concentration decreases as the distance increases, both in vertical distance or in horizontal distance. So mostly the average shape of plume is cone shaped. So you might be seeing the plume changing shapes, but on an average the shape is cone shaped. Further, the rate of dispersion of the plume is a function of atmospheric turbulence. So what happens in the atmosphere really influences the rate of dispersion. Atmospheric turbulence is based around simple meteorological parameters involving, like it would take solar radiation, cloud cover, mean wind speed, and it is and expressed in form of 6 or 7 Pascal stability categories. There are also stability categories which range from class A, which is very unstable condition, which usually occurs during hot sunny conditions with light wind, through like you have classification like F, G, which indicate very stable conditions. Usually such stable conditions occur during cold, still night with clear sky. So you can see in the image the range of the stability class. However, new version of Gaussian plume air dispersal models, for example, like you have AirMod or ADMS-5, are improved version of the turbulent flow in atmospheric boundary layers. So we have seen the principle, but now newer models are coming with the improved concepts. You may know that the maximum ground level concentration from a pollution plume is where the plume touches the ground. So wherever the plume is touching the ground, that means there is maximum ground level concentration. This can happen due to several factors, so such as high pollutant concentrations, because there's pollution is very high, or because of the meteorological conditions, so how the atmosphere is, or because of the surrounding, how is the terrain, topography, the adjoining building, and so on. So this can happen because of the multiple reasons. Usually the maximum ground level concentration stack or elevated source occurs close to the source. So it would happen close to the source. This happens during light wind when the atmosphere is very stable. At these times, considerable vertical mixing happens. So it usually happens on hot summer days. It can also be seen that during light winds, the peak concentration is found further from the source during conditions of increasing atmospheric stability. You can see why it is important to take into account local meteorological conditions at site. So depending on that, your rate of transfer dispersion will vary. Also, whenever tall buildings are there adjoining to the facility, wind can sometimes give rise to high ground level concentration. So that can also happen. Such a situation arises, and you will see why such situation arises, due to the formation of eddies around the building that make the plume touch the ground much closer. In absence of building, these plumes would have not hit the ground. It is usually understood that building downwash problems occurs if the stack height is less than 2.5 times the height of the building above which it projects. So you can see the impact, like how the wind really moves around the building, which causes the pollution to go down. Similar problems may occur if adjacent buildings or hills are within about certain distance, for example 5 stack height of the release point. So such similar situation can happen. In such cases, the buildings can influence the stack emissions. So there can be change in the pattern. Therefore, it's important that the local context should be considered in the modeling. So that's why you see that how different things can change how the pollution travels. So it's very important that you consider the local context. Other situations giving rise to high pollution concentration may be when plumes impact directly on hillside under certain meteorological conditions, or when valley trap emissions during low level inversions. So all these conditions can also impact. So now moving on to road traffic air pollution modeling. So for the prediction purpose, as you can reflect, like we're talking about road traffic, the linear source model I used. The prediction is made at the receptor's level. So the receptor, so we make the prediction at the receptor's level in the surrounding areas. Number of models are designed for the purpose for the road vehicles. So you see UK has a developed ADMS road model, then you can see US has EPA's Cal 3 QHC which is available, and then you can see Caline 4 model, both of which are available as an open source code. So you may also find other proprietary models for traffic flow modeling, and the examples include Enviver, which is also available for the purpose of calculating mass emission. Usually when you do this modeling and when you get the output, the difference in results are taken out. Difference between when you estimate without the project, without the proposed development, with the proposed development. So among those you take out the difference. The results indicate the predicted concentration for each scenario. So a building scenario with project, without project, with alternatives and so on. So you see the difference between them. For this purpose also you will have to consider the local and meteorological data. So you also need to see how it goes with the context when you are comparing the results. There will be a lot of details which you may have to look into. Let us now look into modeling data requirement. What kind of data will be required? So we see that for the modeling purpose you will be requiring emission data. All the numerical dispersion models require emission data, either in form of a specified emission rate. So you can take from the emission rates which are specified for the sources. For example, the amount of pollutant released by per unit of time, or you can measure, or you can take the measure of the level of activity of the source. For example, you can take care of the amount of fuel consumed in a cumulative manner. with the corresponding emission factors, the quantity of pollutant emitted per unit of the activity. Emission rates need not necessarily be exact. So for this purpose, you need not take the exact value, as likely impact of a plant development could be assessed by using the highest likely emissions. So you can take the highest emissions also, and you can do the prediction. The highest values could be like maximum emission limits defined for the operational purpose. So for those figures also you can take and do the calculations. Models can also calculate vehicle emission rates for a specific section of road from input data such as a vehicle flow. So which input data you have already given: vehicle flow, vehicle per day, peak hour value. So with that it will also calculate for all the sections. Average vehicle speed, if you have given input data, vehicle mix, what kind of vehicles are there, and vehicle emission factors. If you are using model for future year prediction, so for the prediction purpose also, then accordingly you have to provide the input data, and you may also account for changes in the technology, changing in the fuel, and changes in the policy in the future time. So when you do prediction for future, you need to take care of those aspects also. So you will require, now moving on, we see that you would also require meteorological data. All models use meteorological data. Some use simple statistical data sets, for example Pascal stability classes, whereas others use more complicated data sets such as hourly sequential data. So rather than just classification, you can have hourly data as well. You have to use the data as per the location and the assessment you are making. So where assessment you have to do and to what detail do you need it. It is suggested that as weather pattern vary from year to year, therefore when modeling is undertaken for large scale industries installation, one should use 3 or 5 years meteorological data and should compare the results. Even CPCB gives you these guidelines, you may look into that. You can see the type of meteorological data required, that is wind speed, wind direction, dry bulb temperature, wet bulb temperature, and so on. You can also see the pollution data, measurement methods and tools used for measuring and collecting these meteorological data. So there's a list which CPCB provides, like how the data has to be collected, how it has to be measured, and what frequency one needs to measure, how many seasons one needs to take. You will be required to note other factors also while taking meteorological data, such as relative height of the meteorological stations, so from where the data has been taken, and then the assessment site, and the potential coastal effects, if any, that all needs to be considered. Further, as discussed before, you will also require to consider terrain topographic data. As you can think of topography, create turbulence at and close to the ground level. This in turn influences the dispersion of pollutants between source and the receptor. So there might be disturbances. The complex model can take account of terrain and topography. So those models can take care of it. The data can be drawn from the survey to create a three-dimensional map of modeling area. This allows for landscape features like, for example, hills, mountains, valley, and even man-made structures such as motorway and embankment and so on in the modeling algorithm. So you can take care of these things. So now we look at the model output. So now we have seen what kind of data is required. Now we're going to look at the model output. Usually the output are short-term pollution impact the output can you can get output of short-term pollution impact, like the highest or the worst case hourly mean concentration, and you would also get like long-term impact, like annual mean concentration. You will be required to compare the outputs with the applicable air quality standards. So when you get the results, you need to compare it with the standards guidelines for your study area as per the local legislation given to you. So then you make the judgment whether it's low, high, what it is. Among many benefits, a significant one about the modeling is that it allows the user to generate graphical outputs. So it's allowing you to take care of a lot of factors. At the same time, it's allowing you the graphical output, such as isoline plots, which can greatly support you to do the assessment and also to communicate the results. And you can see that many newer models now can integrate with GIS, geographical information system, and this allows many other overlay analysis. Now, looking at the model limitations, so what kind of limitations are there? You may reflect that the models are simplification of reality. So in modeling, you are simplifying the reality, you're just putting few numbers of factors there. So it's a simplification of the actual scenario. So there would be limitations and there will be concerns for accuracy and confidence in which you are giving the results or calculating the estimate. You need to clearly state the limitation of the model and assumptions. Whatever you have used, those things should be clearly stated. In all the prediction process and results, there are certain level of uncertainty. You should take note of it and also communicate about it. The accuracy of the output will depend on the quality of input data. So what kind of data you have put, it will depend on them, as well as it will also depend on the algorithm used in the model. So there can be uncertainty because of this, what process you're using and then what kind of data you're giving in. The real check for this purpose to validate is to match the model result with the current baseline conditions in the study area. So you see the actual scenario and you match it with that. You can cross-check the results using the monitored pollutions data as well. There are also guidelines, methodologies to check the road traffic air pollution modeling results, which is developed by UK. So UK has developed a framework for the validation purpose. The prediction made by modeling software for point source are normally validated during the development of the model itself. So when you're developing the model, when the model is developed, that time itself the validation is done. So usually one may not require to compare the results. Now looking at the order effects, in assessing the order effects, both predictive and observational methods can be used. So you can predict also and you can observe also. Predictive methods can involve like a risk-based assessment of the source, where you look at the pathway and the receptor and then you can draw a conclusion. You can have other semi-quantitative assessment. So you can use the screening models or lookup tables to predict the order concentration. So you might see what is the scenario here and compare and do it. And then third is the dispersion modeling, whereby order concentrations are predicted and compared to the benchmark values. So what are the accepted values, you compare with that. So now coming to the significance, how do you really evaluate the significance of your impact? The level of significance is assessed by comparing the predicted change in the area to the air quality standards. So whenever you get the results, you compare it with the air quality standards and then look at the objectives and the guidelines values, and you see how far or ahead or lower you are. Then you evaluate if these outputs are likely to be exceeded at any location. So for any other location, will the value will increase or it will go beyond the standards. After taking into account the existing and the predictive baseline pollution levels, you make a judgment. So if the plant development is predicted to increase pollution levels in access to the close to the air quality standard, then you have to adopt the mitigation measures. So if it is in access, then you have to come to the mitigation measures, how you're going to control that. And those ways you have to take care of it. We'll be looking at the mitigation measures in the later part of our lectures. Now looking at the case study, so this case study has been given to the link to the case study is given, so we'll briefly look into it. You're looking at the EIA of Low Country Corridor West project in Charleston and Northern Charleston, South Carolina in US. The air quality impact analysis focuses on mobile source air toxic, which is MSAT emission. And they're looking at this emission and they're measuring the potential air quality impact on severely economically disadvantaged communities, the neighborhoods there, which are in the immediate vicinity of this particular source. So you're looking at these report, this has been also given to you. You see that, look at the model output, how it looks like and what kind of projections have been done. You look at the kind of data which has been fed there. Then you see the dispersion model. They have selected air mod model here as per the EPA preferences. They have used the model. And then they have also linked the context and terrain. You can see here in this particular, so I've just taken some of the snip from the report. You will see that the model is also providing stretch specific output. You can see here different locations and output on without and with the project. So you can see here how in the bottom rows you can see against each of the images like how the output values are varying and what is the difference between that. So you had talked about the model output, so you can see the model output here and with the scenarios, different scenarios and at the different location. So they have also provided the algorithm for all the scenario. So all the scenario which they studied so you see what kind of information is given. So the link to the case study is provided to you for further details. So summarizing what we covered today, we looked at the impact prediction and the methods which are available to you in this. So we looked at the physical model and expert opinion, we looked at the numerical dispersion models, we looked at the underlying principle of air pollution dispersion modeling, we looked at the road traffic air pollution modeling, then we looked at the what kind of data is needed for modeling purpose, then we looked at the outputs, we looked at the limitation, we also looked at the order effects, and then we just skimmed through a case study which has been given to you for further detailed study. So these were the references and these are the suggested watch and reads because our coverage is very limited. So you can read more if you're interested and explore further. Please feel free to ask questions, let us know about any concerns you have, to share your opinions, experiences and suggestions. Looking forward to interacting and co-learning with you while exploring EIA. Thank you.